Yeah, well, it was a good 9 years.
I'm leaving it. I've thought about correcting it. It actually says, "You're welcome for being married to the goat for 9 years."
Ah. Yeah, you might want to explain that one. Yeah.
No, I'm actually not going to say shit.
No, you're
I'm just going to see how it rolls. And this room's kind of dark and quiet. I might be sleeping in here.
There's no couch in here.
Just come in, you'll be curled up in the corner. Okay. Is it your second time on the podcast?
This would be my third.
Okay. All right.
Although I didn't actually listen to the second one.
No, that's
Maybe
fine.
it doesn't count.
I won't hold that against you.
Chap, honestly, have you listened to any of them?
I do.
Oh,
I don't make it all the way through.
it's that boring? You're like, this is just boring as fuck.
It's actually not boring. I find it really hard to listen to myself for anything more than like 5 to 10
Dude,
minutes.
it's so cringe. I can't do it for more than 5 seconds. So I've never listened to one of these podcasts and I refuse to.
So generally the cadence is I will be like, hey, it's Thursday or Friday. I'm going to go for a run. I'll listen to our podcast. I may get to the stop sign where I generally have to stop and wait for traffic, which is depending on the pace for the day, like somewhere between 7 and 10 minutes away. And then I'm like, and music. So
Did you hear Jackson Ultra Runner?
I did not.
Yeah, he signed up for the 100K, right?
Are you ready for the Tahoe 200?
I can't see his facial expression that clearly,
Well,
but it
It's
doesn't.
the, it's the one everybody else
His
shows.
doesn't
That's what I
eyes are
said.
darting across the back and forth like crazy stuff is being discussed.
All right, are we doing this? Can we hurry the fuck up? I got shit to do.
I'm ready.
What, episode 39. Okay. All right. Welcome back to Roid Rage. This is episode 39. We have Chris, our head of avionics, back on the year three-peat, right?
Three-peat. Yeah,
Okay.
this will be 3.
All right. We're gonna start like designing merch for like how many times you've been on the podcast. That's another thing that Rachel's gonna handle at some point. Today we're obviously going to talk about avionics, specifically how we design electronics to survive in the very forgiving environment called space.
Hold on. I don't even get a call out. Like
Oh yeah,
the
Matt's
greatest host. I've been gone for what? I feel like the last 4 episodes I've been gone.
here.
that true?
It's definitely been noticed.
Yeah, it's definitely. I mean, I got a personal email by a couple people that were like, "Dude, you're the greatest. You're one of the greatest panelists on this podcast. Where have you been?" So
Did you also run those emails through AI detection just to get
Let's
a sense
continue
of,
on,
like,
chap.
Okay. All right. Just asking questions here, man.
How many times have you been on, Matt?
I don't know. Probably 30. I've missed a couple episodes, but I think going forward, I'm going to make a point of being on this episodes as many times as I can.
Maybe we should actually go back and like see like how we perform and like what's the right mix of people.
It's pretty clear when you look at the stats of episode plays versus me being on them. Like I think I 2x the show just being here.
Just okay, cool. Yeah. We might have to like run a little bit of regression analysis over that, but we'll see. All right, let's get back into what we're talking about. So we are going to talk about space and how we design electronics to last in them.
Yeah.
Yeah.
Hopefully.
All right. So how do we start? Like you say, great. You got to build a spacecraft. It's got to have some componentry on there. Where do you start? What are you most worried about?
Well, what am I most worried about? Stuff not working. There's lots of reasons that happens, though, you know.
Okay.
So the space environment, as you call it, very forgiving is not. There's a lot of things that you have to like take into account. You know, there's radiation, of course, cosmic rays and solar winds, and you know, if we were spinning around the Earth in a boring manner, we would have, you know, the Van Allen belts that trap a lot of radiation.
Hold on, can you talk about that, Chris? Because you started off just saying space has this, but I think most of the people, when they think of space, they think of the boring ass space shuttle or the ISS or low Earth orbit.
Yeah. So in low Earth orbit, I just described that environment briefly, right? So, you know, it's a couple 100 miles up roughly, goes up a little higher than that. But most of those orbits are like 90 minutes or so. They go around the Earth every 90 minutes. So in LEO, you heat up and you cool down. You go through a lot of heat cycles, right? You have to charge, you know, you go back behind the Earth from the sun, you're hiding from the sun. So you have to like run on your batteries. So every time you go around, you're cycling thermally, and you're cycling your batteries and all this kind of stuff. But you're also running through the Earth's basically magnetosphere. You know, there's a bunch of charged particles and stuff that comes flying out from the sun. and they get trapped in the Earth's radiation. I'm sorry, the Earth's magnetic, you know, field lines basically, and they kind of bounce back and forth between the poles. It's what makes your aurora borealis or your aurora australis, if you happen to be listening from the southern hemisphere. But you run through those, and there's a lot worse radiation there because it kind of concentrates the particles, so you get a lot. So we do get a little bit of a break from that by getting out further, now because we're not running through those belts all the time. But instead of that environment, we have other challenges, right? So we still have to deal with the solar wind, which isn't too bad unless we have like a coronal mass ejection or a solar flare or something like that.
And define. Most people are probably familiar with the term. What is solar wind?
Solar wind is like a collection of particles that the sun kind of radiates out, right?
Okay.
It pushes out, protons and electrons, but mostly protons and some heavy ions, some of them.
Yep.
But they generally have a little bit less energy than what comes when you get a coronal mass ejection or that's really the worst one that hits. Cosmic rays, galactic cosmic radiation, is kind of another thing entirely, and those particles can be going really fast and have a huge amount of energy, but there's a lot less of them, so we don't have to consider them as much, but we have to consider the particles that come at us at a coronal mass ejection, for example. That's like I said, that's the worst case, and they have some higher energy, again, protons and heavy ions and stuff. That are kind of hitting you all the time, right? So on one side of the Earth, it kind of, if you look at the Earth's magnetosphere, the side facing the sun is like kind of crunched up, and the side tailing off the other side of the Earth is elongated, and that's really because the solar wind is actually pushing, it's an interaction between that, and so it's kind of pushing all that out toward the back, right?
It looks like Sonic the Hedgehog. Remember when he used to go in the little ball
does.
and you go forward? It kind of looks like that.
It does look like that a lot.
And it really is. It's what you would also see if you were just to put a ball in water and move it quickly. You see that kind of cavitation after. It's actually the same thing that happens with solar wind, right? It's all these. It's like this field of particles that we are pushing the Earth through, and so you'll see this kind of like curvature go around the Earth and tail off after.
Yep.
Right, and that's why we live on Earth, right? Because we have the magnetosphere.
I just live here because I was born here.
Well, yeah, but I mean, we wouldn't have been born here. None of us would have if we didn't have our magnetic magnetosphere to protect us. It's like
just to be clear, Matt interpreted that question as like, I just haven't figured out a way to get out yet.
Yeah,
like,
I see.
Yeah.
I'm trying to leave it. But we left out, I mean, what that causes is this, what we call the Van Allen belts, right? These series of belts that are the protection to Earth. And when you're in low Earth orbit, what's nice about low Earth orbit are you are below the Van Allen belts, which, to be clear, also when we see that magnetosphere form, or the heliosphere form, I should call it, what you get is this compression of particles. So you actually get really dense radiation in what are called the Van Allen belts. And I'm not even going to try to describe them. You can go look at pictures of what they look like. They've been measured pretty extensively. In fact, the Van Allen belts are the first measurement we did as a country. That was our first launch vehicle, or our first satellite we sent out. Measured the Van Allen belts. That's where we found them. But we get a lot of protection because we're under them in low Earth orbit. We said, that's not really cool. Low Earth orbit's boring. Let's go past the Van Allen belts.
Right.
And so that's where we run into a lot of our problems. But to be clear, we are not operating in the Van Allen belts.
Right.
It's very difficult to operate in the Van Allen belts. The radiation is much, much higher. The radiation that we get on just a standard kind of particle count is about 3 times higher in deep space than it is in LEO. So it's not that much, right? It's not a billion times worse. It can be if you go through a Van Allen belt.
Right, and there's a couple of caveats to that, right? If you have a higher inclination, or even a polar orbit, like there are a lot of LEO satellites that are in a polar orbit, and they go through the Van Allen belts like twice a rotation, every orbit, right? But if you're more less inclined, meaning more toward the equator, you're kind of protected from that, right? They also have other problems that we don't have to deal with, which is atomic oxygen, right? So you have these.
What is that?
It's just so when UV rays hit, they kind of break the we're normally O2, that's what we breathe, right? But they get hit and they kind of break apart. But the only important part is that as you're flying through all that stuff, and that can go up quite high, higher than low Earth, than the 200-mile low Earth orbit threshold kind of thing. it really erodes a lot of the things on the spacecraft, right?
Got it.
So like you put your cover glass on, for example, on your solar panels, and it gets eaten away by atomic oxygen.
You gotta love these fucking engineering guys, right? Chris is like atomic oxygen. You mean just oxygen?
Yeah,
Like,
just oxygen.
It's just called oxygen. Why do we call it atomic oxygen, Chris?
I think
I'm
they
gonna
like
start
to-
using that word for
It
shit.
does sound it does sound a lot
sounds-
better,
it
and it's
sounds
like
way
it's a
cooler.
better rock band name, like
Yeah.
Atomic Oxygen. Yeah,
AO, right? So
Yeah.
everybody loves the abbreviation. I think that's what it is. And I know you're a big fan of abbreviations. So I
Love
think
them.
they really
Yeah.
like the AO thing. I don't know. It's better than O. I don't know.
But you did talk about one thing, which is the coronal mass ejections, aka solar flares,
Right.
which have different classifications on them. And
Yes.
I think it's really important to understand actually the decisions we made very early on in building our spacecraft for the potential for a solar flare to hit, which is X-class solar flare is actually the biggest solar flare we can get that hit. And if that is to hit our spacecraft, what we'll do from the Earth is just wave goodbye to it.
Okay.
There's really no protection you could do at a high level. I think maybe one of the only spacecraft built to handle that much is probably the Juno spacecraft.
Yeah, definitely the ones that go around Jupiter are the ones that are most.
Jupiter's a
radiation
really,
hardened.
really, it produces its own radiation. It's an extremely radiation heavy environment. I think it's like 20 millirads or some unit like that.
Some number I'm scared
That's
to look
massive.
at. Right.
It is massive. And so orbiting Jupiter is very, very difficult. That's why like the Juno spacecraft that is orbiting Jupiter right now, and unless it gets canceled, is one, it was built in a very, very special way to handle that much radiation.
Yep.
Right.
We can't do that cost effectively. Actually, there's really just no way in the physics realm to build something that can handle that much radiation and still build it in a commercial sense.
Right. I mean, if we had a strong coronal mass ejection coming at us, the best we could do is shut down as much as we possibly could and hope. Right.
But we don't get any advance warning of that.
You do
we do.
for a coronal mass. Yeah.
Okay.
It takes a while. I mean, they can be observed, but the particles take a little bit longer. They come faster than the solar winds
Okay.
do, but they don't come at the speed of light. So
Okay.
you do have a warning. Now, whether or not we're capable of talking to the spacecraft at that amount of time and shutting it down, I'm not sure. I haven't done the timing on it, but
Okay.
but generally, those big ones are rare,
Yep.
right? They don't happen.
Yeah,
often.
and the sun also has solar cycles. So there's
Yeah.
certain times where coronal mass ejections are more likely to happen as far as less. I mean, think about it. Even when we sent the first astronauts or all the astronauts to the moon, if they would have been hit by a solar flare, they probably would have died instantly or died very quickly. Like, it's just not something you can realistically protect against. And I don't think if Neil Armstrong and Buzz Aldrin and Michael Collins, I'm not sure what you can't shut a human down. So
No, just they need a force field,
yeah, they need a force field
which
and
doesn't exist, right?
not
Not with
publicly.
that attitude.
Yeah, well, not
Yeah.
yet. I mean, maybe one day.
All right, so we've got solar flares, we've got radiation, we've got solar winds. What else are we thinking? What else am I missing in that list of?
From radiation standpoint,
Yeah.
well, you didn't mention the galactic cosmic rays, and those
Sorry.
those are basically any atom,
Yep.
right? Just anything that's created in stars, which is basically everything. And with the different relative speeds of things in the galaxy, I mean, we're bathed in these cosmic galactic rays, and there's nothing that stops them.
Yep.
They're just going too fast. They can go, right through the magnetosphere and all that stuff, and there's really no protecting from that. So hopefully they just pass right through you and they don't mess your electronics up. But like I said, they're the flux of them, which is just basically how much of them is coming in over a given area over a given amount of time, is pretty low. So we don't necessarily, A, we can't do a lot about it, and B, you don't really have to do much.
Yeah, I mean, this radiation just doesn't exist in space. It also exists on the surface of the planet.
Right.
We can't ignore it. So we, as humans, are hit with we're also hit with the solar wind, right?
Right.
I mean, if you've ever been sunburnt, what do you think that comes from? It's not made up. Like, that's what you're getting. You're getting that radiation dose as it comes through. It's also why server farms go down a lot, is because of radiation that hits them. It's the same problem we have in space. And a big reason that we're able to build spacecraft the way we are today is because actually of server farms, right? That technology to have higher uptime has led to us being able to buy computer chips that have much higher radiation tolerance for space.
Cool. So it's clear, like everybody knows what a sunburn is. What is the spacecraft equivalent of a sunburn?
Well, the damaging things that happen is, I think, what you're going after. So for your electronics, you've got basically two blanket things that come from radiation. You have single event effects, which is basically a particle comes in and it hits your electronics in some kind of squishy zone, and it can cause a bit flip. So you have a
Okay.
1 go to a 0 go to a 1,
Yep.
something like that. Or you can that can cause your memory to get corrupted, or it can cause a transient event. So you send a signal going through your system that wasn't.
Well,
what
hold
it's
on.
supposed to
I
be.
want to back up a little bit. Those, what we call about single event upsets and single event latch ups, are really responding to what happens in transistors.
Yes.
There's a lot of other problems that happen on a spacecraft, but what you're describing is solely focused on transistors, which are our main memory, our
Right.
cache memory, our processors, and probably the biggest footprint on the boards.
Yes, yes, but they're different. There are other single event effects. Single event burnout. You can get single event gate rupture. Sometimes it can hit it and it can change the charge that it a certain thing, or flip the state of a transistor. It can also hit certain areas where you can actually break down the gate oxide and have catastrophic effects. You can have things like single event latch up, which you basically hit a transistor at a sensitive spot and it turns on just completely.
Okay.
And you can get damaged that way.
Yep.
So you can either, we try to get electronics that aren't like prone to that kind of a thing. Or you have to design around it and kind of find a way to either limit the current that you would get from something like that by, something as stupid as putting a resistor in line with the power system, so you can limit your current or something like that. And then you got to recover somehow. You've got to cycle power. You've got to be able to detect. So a lot of that is basically protections for that is basically monitoring the current, making sure if you have something go over current, you're like shutting it down and starting back over. For memory stuff, you just have to be you have to be able to handle certain number of upsets, and they come in, and you can do, if you have a lot of test data and you know exactly what your environment looks like, you can run a lot of statistics and figure out how many bit error you're going to have.
Well, and memory, what we do on spacecraft for memory is we actually use 10-bit wide memory. So on a normal computer, you're going to have 8-bit wide memory. And that has no checking on it. We have 10-bit wide memory, where 2 of those bits are actually allocated to checking the 8 bits to see if something changed, right? So it's you can think of it as like a checksum after we're checking parity in this, and we can correct it. So this is referred to as ECC, or error correction code memory. That's actually a huge thing. And what it comes down to when you're looking at radiation is actually surface area facing the sun, to be very clear. And if you look at a computer, one of the biggest surface areas we have is actually the main memory. So that is one of the things, we will not fly regular main memory. It has to be error correction code main memory. We'll take the 10-bit versus 8-bit wide hit all day long. It's too risky.
Yep.
The next biggest thing on a computer chip is on the actual die of a processor is going to be the caches, which are memory that go directly into the CPU. Same thing there. We only choose processors with L2 cache that have error correction code. Then you look at like L1 cache, which is very close to the arithmetic logic units, right, and how processors work. A lot of times those are never built with 10-bit wide memory. They're built with only 8-bit wide memory blocks. And so on those, what we will do in certain cases, depending on our testing goes, actually skip them. So a lot of them will have what's called L1 cache pass-through.
Got it.
We just disable it. And we'll take the hit count on moving memory out of L2 cache, which is much slower, but it doesn't matter because we know it'll move and it'll work. We don't want something getting corrupted right before it goes into the processor. That output would be totally bad.
Yeah. So other than single event effects, which is like a whole slew of things that can happen, you have like total dose kind of issues, right? And there's a couple of different ways that affects it. So you have total ionizing dose, which is what you hear a lot. You say, you got 20K rads of total dose or 100K rads of total dose for some more stuff.
Total dose, you mean like over some time scale, how much radiation have you had in the...
Over the entirety of the time scale, right? It's kind of a cumulative effect. And basically in the total dose, total ionizing dose, it's a kind of a clue in the name, is you're basically getting charges trapped in the wrong places inside of your parts, right? So, if you were looking at a band gap, in a drawing, you would have little charges in between the band somewhere where you aren't expecting it. Because over course of time, and the more that you get, eventually you can cause the part to not behave. You can change like levels of how it reacts and whatnot. And when it turns on and off, you can switch the levels and change the way that it reacts. And so when you hit the total dose number, for total ionizing dose, it just stops working right.
Got it.
And that's one way that this affects it. The other one is called the destructive damage, TDD, or I can't remember the acronym off the top of my head. DDD, I don't know.
Okay.
Basically, it's when a particle comes in and it slams in. The silicon, or basically all the semiconductor chips are made with crystal lattices. The whole chip is made. They take a crystal lattice and then we bombard it with stuff to dope it, which basically knocks a silicon atom, if we're talking about silicon, out of the way and puts the doping material in there. But in space or with any kind of radiation, you have a particle come in and you can actually hit the lattice. You hit an atom that's in the lattice in the right spot and you knock it out, right? And that's a destructive, thing. And after a while, you get so much damage to the structure, to the crystal lattice, that the part won't work either. We're a little less concerned about that because mostly TID, the ionizing dose is kind of worse.
Got it.
And that's what that's why we kind of focus in on that.
Well, and we can also measure the ionizing dose pretty well. We understand what the solar winds are. We understand what our MOSFETs can handle, how much before they charge up, and essentially that the gate drain and source are connected now. And essentially you don't have a doped material anymore, right, for a transistor. And like that means that it's not a transistor and it won't switch. And we can measure this pretty well, and we can also test it pretty well.
Yeah.
I mean, that's, I think, the biggest thing when it comes to total ionizing dose. We can go test this easily, not necessarily cheaply, but easily. And the way we do it
It's
is
cheap when you're talking about radiation testing.
yes. So the way we do it for TID is we go to cancer treatment centers and we use proton beam. Right?
Okay.
You've heard of like Cedars-Sinai. Whenever I watch a football game, you always get like all these medicine commercials. Right? I don't know about you guys, but I'm like, dude, what the hell's going on? They always have like the advertised proton beam therapy. Like, I wish if I had cancer, they don't have to advertise that shit, but they do. And that's the same thing we use. So we just go at night when people aren't getting treatments, and we'll put our machine, we'll put our flight computers in there or whatever, and just bombard the shit out of them with proton beams and test them till failure always. We want to see how much that takes to fail. The high energy particles, actually, it's really interesting that the testing for this is usually done at places like the National Ignition Facility.
Okay.
So the NIF at Lawrence Livermore actually does a subset of high energy particle beam testing. I'm not a fucking nuclear physicist person, but for some reason when they do fission or fusion or whatever it is, and they shoot that little thing and they get power positive reaction, and I don't understand what it even means, that shoots out high energy particles that they will test electronics with.
Yeah, that's the heavy ion beam testing, and that's the most expensive form of radiation testing you can do on electronics. It's very complicated. You have to remove the lid on the packages a lot because the beams won't penetrate very far, so you expose the dye, and then you have problems with cooling it. Sometimes you have to like shoot liquid nitrogen on it to keep it cold while it's operating. And there's only a couple of facilities, 2 or 3 facilities that do that in the country. And the time is very expensive and the prep is very hard.
And the probability of it happening on our die, especially with our orientation to the sun and our probability here over a 3-year mission, is actually pretty low.
Yeah.
What does orientation have to do with it?
So again, it all comes down to surface area. And so if your surface area is facing, what it comes down to is solar wind versus surface area. Solar wind is going one direction. So if you take a computer chip and put it directly perpendicular to the solar wind, you're maximizing the surface area facing the sun. You're maximizing both the total and the percent you're going to get heavy ions hitting it. Now, if you turn it completely parallel with the sun and the solar wind, right, and it's in plane with it, you actually minimize that. But you also don't want to do that because if you're perfectly parallel and you get a heavy ion, you can get one that actually just takes out your entire chip, right? Because it can bombard all the way through. So you want to be at a very slight angle off of what the solar wind is to minimize the cross-sectional area, but also maximize the chance that you don't take out multiple transistors with one heavy ion.
Yeah, it also increases the depth that it has to go, right? Because it's coming in at an angle. It's got
Depth
more
through the actual body of the spacecraft itself.
The spacecraft itself and the dye,
shielding
part, right?
And the shielding. I mean, if you take a piece of aluminum that's 4 millimeters thick and you turn it this way, like that particle going straight through is now going in a triangle shape, right? And so that, whatever that is, the hypotenuse is longer than the A side and Pythagorean.
Some geometry stuff. Yeah.
We met with Pythagorean.
We need to get GNC in here to talk about angles and stuff.
Whatever. Get Armand in here. He'll answer it. Yeah.
Okay. So it sounds like positioning is one way that we can start to not test, but actually protect the electronics. Like, how do you think about protecting electronics in this environment?
So, I mean, well, it starts with picking the right parts. We use parts that we have a reasonable reasonable belief are going to be good, right?
Yep.
And then we test them. Proton beam test them to get
What is a
single event effects
reasonable belief? Like, how do you quantify that?
I reasonably believe that the MOSFETs we're using for our power, the GaN FETs are going to be reasonably hard.
Okay.
And that's just because that type of FET doesn't seem to react. It reacts well to radiation,
Okay.
right?
Chris is lying to you so hard right now. The other thing is, multiple people have been to space and like they produce results on how much they can handle. So the way you figure that out is you just go on the internet and type in your part number and look at how much dosage it can have, and it'll usually have some data there.
Sometimes,
But I like Chris when he says, he just thinks of,
I just think
he
of
just
stuff
goes with his
and-
gut.
Yeah. A lot of that data is really hard because a lot of people really protect that data, so it's not easy to come by all the time. But what we want to do is pick parts that we think are going to do as well as we can, and then go test the system
Yep.
Under a proton beam and see if we're getting because that'll help us out with the single event effects.
Yep.
We can see what kind of bit error rates we'll get with the protons because let's face it, we're not going to go spend all that money to go and do a heavy ion testing for this, right? And do all that. So we do as best as we can, and the protons are a lot of what they see, right? It's actually probably the most numerous particle that's going to hit us by a pretty big shot, wide margin as far as the fluxes go.
Yep.
So we do what we can with our circuit design to protect against this. We do what we need to with redundancy, right, to make sure that if something goes down, we have another system that can use. And we also the other thing that's really important is to make sure that you don't design something in your circuit that's going to bring everything down, right? So if I get a hit on a MOSFET and it suddenly shorts out, I need to make sure that I don't bring my entire spacecraft bus down.
Got it.
With that, right? So that's it's a combination of picking the right parts, testing the right parts, and putting them in the right architecture to protect yourself from bad stuff happening.
Got it.
It's also it's not like a threshold. We don't just say like, oh, if you can hold a radiation dose of more than 50 kilorats, like we'll fly you or not. The parts actually aren't all even. So we do have a microprocessor that's super radiation hardened, and that's intentional because it controls the power system.
Right.
And what we don't want to have happen is us get a single event flip on something, and all of a sudden like our power system overloads and burns everything up. That's not necessarily the same with the processor that'll process GNC. We're okay with it, if we don't want it to restart, obviously, but let's say once a week it gets hit and it needs to reset. Okay, we can handle that and we can build that in. Not necessarily true when you have 2 kilowatts of power coming in.
Right, and that's really important. We're new space, so we like to use as many COTS parts as we can, as cheaply as we can possibly do it. But we need the mission to work too, and for that to happen, and for you to be able to recover anything, your power has to work, right? So there are some pretty expensive parts in our power system, right? That's definitely the most rad hard system that we have, and I think one day.
Oh, and the radio, the power and the radio both share a lot of expensive shit.
Yeah, right. The radio's also made to be rad hard. Too, right, and that's one of the reasons. Radios are expensive to begin with, but then you make it rad hard, and it gets even.
I mean, the
more
radio
expensive.
is one of the few components. So when we talk about flight heritage, we talk about deep space flight heritage. Like there's very few components we can buy for deep space flight heritage. Everybody going to LEO is cheating because you can buy that shit all over the place. But the radio is one of the few components that has flown to deep space and we have heritage on. And so it'll be, I have a lot more confidence the radio is going to work with no problems than maybe the rest of it.
Yeah, and I take offense to that. 'Cause
that was meant to be offensive. That's why I looked at you when I said it.
I was going to ask you how you felt about that.
So the other thing is, on top of that, the architecture and picking the right parts and going to testing, we shield. You make sure that you have enough, some amount of aluminum. I think it turns out to be like 3 millimeters. You get like this nice
3.5.
3.5. Well, you get this nice curve, where you stop getting benefit from it around that point. It's kind of a curve.
Yep.
So if you got 6 millimeters or 3.5, it's about the same. So. And with everything being weight sensitive, of course, we want to minimize the amount of weight. So if it doesn't do us any good, we don't do it anymore, right?
Yep.
So I guess that's basically how you protect the electronics from radiation in space.
Got it.
Yeah,
So
to be clear, there's not much more you can there is some on Juno. They did some really cool stuff, and some old processors did. But there's not really much more you can do. You can increase the shielding. You can buy higher radiation dose parts. Like, you can spend more on space rated parts and things like this. But it's about all you can really do. There's no other technologies. Like, we haven't invented magnetic force fields yet or things like this. I mean, people have theorized them, and they can, from the realm of physics, like, you could do it. The Earth does it. But it's not something we can actually put on a spacecraft.
Right. Yeah. There is only so much we can do. Yeah.
Yet.
Okay, so that takes care of most of the actual core piece of the electronics.
Yeah.
How much do you think about what the spacecraft is made of? Like, because this is all housed within the larger body,
Right.
made of metal and composite.
Yeah, I joke with the structures team that they're building the biggest electronic component in the system, right? And they really are, because it's the way that the grounds for the whole spacecraft are put together, and then you have the same issue with the spacecraft as you do with the electronics. It's bathed in this solar wind and these charged particles all over the place. So you've got to make sure that you don't have a large buildup of charged particles on any part of the spacecraft, because let's say you
large
have
in this case.
Let's be honest. Let's be honest for a second here. I think they make this all up, chap. We're in these meetings, and we're like, yeah, we're going to paint the panel white. And Chris is like, no, it needs to be white but have particles in it so it can be conductive.
Yes. This is very important, actually. And you can do some math to figure this out, because you've got the flux of the particles coming in. This is actually pretty straightforward. You know what the flux of, which is, again, it's just the amount of particles coming in to a given area in a given amount of time. And you know how much positive charge you're going to get from your protons, and negative charge you can get from your electrons and whatnot. But they build up on a surface. And if the surface is a dielectric, it doesn't conduct, then they just sit there until you can get incredibly high voltages. In geostationary satellites can have 20,000 volt discharges.
Just wow. Okay.
So you
Is that
want to
bad?
make. Yes, it's bad if it's in the bad spot, right? It's all a matter of
See
where.
what I'm talking about? How I think they just make it up. They're like 20,000 kilovolt. Like, a taser has 20,000 volts. Who cares?
Well,
it
if
doesn't
I were,
do anything.
Have you been tased?
Yeah,
People who get
it's
tased
mediocre.
care.
Well, whatever. But it's not going to kill you.
So I've got some nice pictures in the training that you'll love that we're going to go over.
Oh God, we've got training.
Yeah, in our all hands meeting that shows pictures of what happens to these teeny tiny electronic parts when you zap them with large amounts of power.
Yeah.
Right, and you basically can melt shit inside the part.
Okay.
And that's what happens if you.
But hold on, you just said this is on the outside of the spaceship, and now you're saying it's going to shoot laser beams in the inside of the spaceship?
It's not all on the outside of the spacecraft, right? So all of my electronics are attached to the spacecraft structure, right? So if I have discharges in a place that's not a good place, well, we'll talk about charges inside the spacecraft in a minute, but for the moment, we want to seal up the outside so that we don't have. You want to prevent as much as you can from getting inside, because if I had one of these little discharges happen into my harness, that's going straight. It's like a straight shot to my electronics, and you can easily burn out a transceiver or anything that's attached to that harness right on the inside. So, but the same thing on the outside, because I have wires on the outside. I know it sounds amazing, but we have solar panels, for example, on the outside. I have cameras that look outside. I have radios, antennas. So there's all kinds of things. We try to seal up the spacecraft as much as we can.
But it's not.
But you can't completely seal it up, because stuff has to be on the outside. So if you get a discharge, for example, going from the antenna, you've got a little harness going from the antenna inside to the radio system, you can get a discharge that arcs over to that cable, and then you can blow out your very expensive deep space radio, right?
Got it.
But by the same token, if I had a discharge from my solar panel directly to the aluminum, substrate that it's on, that's probably not a big deal, because there's nothing there to necessarily hurt. So you just have to be very careful when you're putting together. The solar panel is a little bit harder, because there's all kinds of dielectric materials that go next, and if you have dielectric material next to conductive material, that's where you're going to get a buildup, and you're going to get an arc to discharge.
Got it. So how do you manage discharges from that are external, and then we'll talk about the ones that are internal.
You you cover your spacecraft as much as you possibly can with conductive material,
Okay.
which is why I want the paint to be somewhat conductive. It doesn't
Got
have to be super conductive.
Spray paint at Home Depot's $5. Chris wants to spend like, how much is this conductive fucking paint?
I don't know. I didn't ask. It's more It's less expensive than a
Typical.
failed mission.
Yeah, typical.
That's fair. It's a great. Yeah, it's a less expensive than the failed mission. That
Yeah.
is definitively true.
Yeah, that's basically the justification for spending some money on some paint.
Okay. So we have really expensive spray paint that we use to fix the.
Oh, no, Chef.
discharges.
This isn't spray paint. This shit's got to be baked on the panels before we even get the panels. So, yeah.
Oh.
Yeah, let's take a time out. This
There's
is
a,
not.
there's a whole like
There's
I'm
a
gonna date
whole-
myself like pimp my ride like episode here where we
Exhibit
can just
came
go
out
through.
and was like, dude, we got to get this panel,
you know what?
coat it, bake it, put some gold flake in it or some shit.
So
and then
Rachel, can you
it'll
figure
be
out what
happy for
exhibit's
Chris.
doing these days? Because I'm pretty sure if we did like a pimp my ride spacecraft style, like
I'm pretty sure if we just emailed Exhibit and was like, yo, you want to come on the podcast? He probably would. It's not like he's doing much.
there's an opportunity here, Rachel. I'll let you figure that out. Okay, so sorry, use the correct terminology. We bake this onto the external panels. Anything else we do for the external protection of the electronics?
Well, I mean, we do have to have a place for our charge to go,
Okay.
right? So as we're flying through space, we're kind of like, especially with our electric propulsion system, we're
Mhm.
basically making a whole bunch of plasma.
Mhm.
There's plasma there. So the whole spacecraft is like bathed in this sheath, to use the technical term, of plasma,
Okay.
which is basically just a bunch of charged particles, hanging out
Mhm.
right around there. And on the other side of that little sheath is space.
Yep.
And that's ground. It's hard to come to terms with that the ground for your plasma and your spacecraft is actually on the other side of that little sheath. It's just space.
Yeah.
So you build up charge. You want to be able to release that. So the conductive surfaces on the spacecraft will allow it to basically discharge into that. It's the path to ground. So we trail off. As we're shooting off our positively charged xenon particles, the electric propulsion system also just trails off a bunch of like electrons. So we're
Okay.
not charging up at the same time, and so it kind of in the magic of space,
Yep.
all of those particles kind of cancel out. And as you build up, and it does all kinds of weird things to the potentials with the Hall thruster and whatnot. But basically, it comes to some kind of equilibrium where the charged particles will leave your spacecraft magically.
Yep.
Are those atomic electrons?
They are not,
Hmm.
because they're only electrons. Now, if
Right.
you have a proton, you could call that a atomic
Atomic hydrogen?
Yeah,
Okay.
if you want to be
Good
fancy.
to know.
Okay. Any materials so you mentioned aluminum right now. Boards are going to be composite with this paint, correct?
The what?
The panels, sorry.
The panels, yeah.
Yes.
I didn't pick the paint, by the way. I just said it had to be conductive.
Are there how much influence do you have into like the actual choice of materials? And are there materials where you're like, please don't use that on the spacecraft?
I just try to give requirements, what it needs to be. Like I need 10 to the whatever conductivity or something like that. I don't say use this or use that unless I have an idea. It's like, use this magic material that makes everything better. I don't have a lot of those.
Got it.
And I'm not a material scientist, I just know what the property needs to be, right?
Got it.
I care about conductivity of the surface
Yep.
or some such thing, or I care that I have 3.5 millimeters of aluminum shielding on the spacecraft or whatnot, stuff like that.
Okay.
I try to not over specify stuff, especially as the electrical guy.
Got it. You say that as if like you're a second class citizen on this.
No. I let them deal with that
Got it.
small stuff.
He's actually saying it like he's king. He's like,
Yeah,
I'll let
exactly.
the other people deal with that problem.
Exactly. Here's what it needs to do. Now go make it happen.
Yeah. Okay. So we have not gone to the internal discharges yet.
No. So we try to limit those
Okay.
as much as you possibly can. And so you want to try to make the spacecraft a Faraday cage, so to speak, so that plasma and that sheet
Can you
doesn't
explain
get
what a
inside.
Faraday cage is? Because I think a lot of people use this term, and very few people actually understand what it is.
So a Faraday cage is it's like my house. I have a house that's built and has like aluminum siding on
Yep.
it. So we get terrible phone reception
Reception,
inside the house. But basically, it's a metal box
Yeah.
that's, kind of blocks EM waves,
Okay.
right? So
Yep.
it's like a big ground,
Yeah.
and you have like radio waves or whatever coming in, and they kind of hit that, and they don't pass through very well.
Okay.
And it doesn't have to be an actual solid metal box.
Yep.
You can have holes in it, but it will be a Faraday cage to certain frequencies,
Got it.
right? So, for the frequency I care about up to whatever, that really determines how big of a hole that I can have. 'Cause
Got it. Okay.
There's like a frequency response to a hole. I know it sounds kind of strange, but they're all just tiny waveguides,
Yep.
and they allow certain frequencies in. Above a certain amount, they'll just pass right through. But we try to keep as much of the electronic EM waves out of the spacecraft, and that will allow us to not have a whole bunch of charge. But at the same time, you're definitely going to have charged particles inside, because there's
Yep.
a couple of different ways that happens. One of them being that something with enough energy can just pass right through,
Yep.
right, and end up depositing inside. Like I was talking about those harnesses a minute ago. If I have a high energy particle come in, it can pass right through the spacecraft shell and land in the dielectric material of the harness, for
Yeah.
example, and deposit the charge there. And then you can also have secondary radiation. The Bromstrong, I don't remember the exact word, some fancy word that's basically secondary. You basically, the particle will come in at such an energy, and you'll hit stuff on the way in, and you'll scatter, and you have
Got it.
secondary charged
Yep.
particles get knocked out of where they were.
Okay.
And those can deposit inside
Yep.
of the spacecraft. But we try to ground everything. A lot of it has to do with grounding and making sure that we have nowhere for you don't want any floating metal in the spacecraft, or as little as possible. There's like all kinds of guidelines of how small you can have, but basically everywhere there's a piece of metal, whether on the board or on a piece of the chassis for the boxes or whatever for the electronics, you basically try to tie all that down so that you can't build up charge there.
Yep.
So, and then like on our harnesses, we try to, you want to try to sheathe them in metal, so that if you do have a discharge, it goes to that, and then can get dissipated into the spacecraft structure. Because all the harnesses are basically, the outside of the harnesses are basically tied to the chassis, right? And all the boxes are tied to the chassis. By the chassis, I mean the metal of the spacecraft, right? But yeah, so we basically try to give them all nice paths to go through.
Okay.
But there's also ways, we also have like protections on, when we can, we have protections on the electronics, right? So for our 422 lines, our RS-422 lines, for example, they'll have like little transorb diodes or whatever you want to call it, that basically if you get, it'll dissipate an ESD strike, so to speak. So
What's
you
an
get
ESD?
Electrostatic discharge.
Okay.
It's basically it's basically when the charge builds up in a place, and then it has that little arc breakdown to somewhere else. That's a discharge.
Okay.
And this is an electrostatic, and they call it that fancy word because it's basically charge that just sits there until it doesn't, and then it discharges.
It's a made-up word by electrical
I
engineers.
know.
Get paid more.
We have people here that think there's big ESD, that it's a conspiracy that sells like straps and
add it to the list of things that we got to worry about.
all
then.
kinds of stuff.
Okay.
Right? It's a cabal. I get a paycheck from them once a year. It's a royalty for.
You get a side check?
Oh
A
yeah,
little side,
for signing on to big ESD and yeah, so it's a big scam. But no, really. So yeah, that's basically what we do. Inside. It's, well, I don't even want to talk about ESD.
We joke about it, but ESD is actually a really big deal for what we do. So, I mean, it's actually kind of interesting to think about. Every time you grab your iPhone to make a call, like you actually make an electrical connection with the phone, and usually you put little tiny holes inside the phone. And so on all those little chips or to the outside case, you're actually blowing little holes in it, then go through. And at one atmosphere, when we have this much air around us and the resistivity between those pieces of metal and air are there, it doesn't create a problem. But as you go and remove the atmosphere, And as you go through it, you can have this become a huge problem. In fact, a lot of spacecraft and rockets have failed from what's called corona arcing, which is when you just lower the atmosphere right down to where arcs can happen. I mean, this is a famous way that quite a few rockets have actually failed. Spacecraft have the same thing. In ESD, when you pick up a board on the table, you may not realize it, but you just blew a little hole in that board. Yeah. And when the atmosphere disappears, that little hole may be the reason between that board living and dying.
Got it.
And that's why we care so much about it.
Yeah, it's actually it's an interesting topic that you can go way down the rabbit hole. But there's a Passion curve. It's basically as you remove the oxygen or the air from an environment, there's a minimum that you get to at a certain pressure, and that's where you have a real problem. Like you can have arc breakdowns and whatnot. Once you actually get all the way out to space and you're back in a vacuum, you're better. Got it. It's all good. And when you start out on Earth, so you start out on Earth and you have one set of, you have one amount of like dielectric withstand voltage that air will take, and then it's nearly the same up, in vacuum because there's nothing really for it to discharge through. But in between, there's a danger zone.
Got it.
Where the minimum, you hit the minimum on this dielectric withstand voltage, and that can cause all kinds of problems. For us, from a designing the spacecraft standpoint, it's easier because we're turned off right during this portion because we're required to be off by our launch provider, right? So we have to be turned off. So we don't have to worry about that as much, right? We do have to worry about how big the holes are in our boxes, so we don't like blow up like a balloon and pop. So there's kind of mechanical stressors that go on to evacuating the air.
Got it.
You just got to make sure that you have enough holes in it. But the holes are, I told you about the Faraday cage before, right?
Yep.
So if I were going to be able to make a perfect Faraday cage, it would be completely sealed up. But if I made it completely sealed up, it would pop when it launches. So it's kind of like a trade-off, like a lot of engineering and a lot of spaces. So I basically tell them, I basically had to go to the mechanical engineers and said, this is how big your holes can be. And now you have to put enough of those holes that are that big, that are basically because I want to keep this frequency out and everything below out of this box or inside the box is actually more the case. But then they have to put enough holes of that size in the box so that it doesn't like pop when we're going up. So there's all kinds of environmental issues, that we have to deal with.
Cool.
Like that.
Awesome. So this is super interesting about how you think about both from like the board and also just like the actual structure that you're building. Next milestone for you is actually integrating all the avionics box and starting to do testing there, right? Okay.
Yeah.
Well, Rachel, we then have to make sure that we have Chris back after that so that we can talk about all the ways in which we messed up the Faraday cage and all the ways in which it went well.
Yeah.
Cool. All right. I guess with that, we're going to go into mailbag for today. And then, Chris, remember that you get to ask Matt, me, but it's probably better to do Matt, a question at the end of mailbag. That's a new feature since the last time you were on. So
I hadn't thought of this.
Well, start
that's
ruminating.
the whole point. We don't tell you till the end because then you have time to think about it. I don't want like some heavy hitters.
All right. Let's start with Micah. Micah says, how are you contacting and holding onto the asteroid? Have any rock climbers been consulted? Perhaps a harpoon tether could be shot into the asteroid and reeled in. My vote is for the harpoon, just to be clear.
Did you guys watch that Alex Honnold guy free solo up whatever it was in Yosemite?
It was very uncomfortable watch.
Yeah.
I did watch it. I will never
It was
watch
terrifying, right?
Yeah.
I would never, I wouldn't free solo this wall. I'm not, what the hell? You're 3,000 feet in the air, just like, dude.
I was uncomfortable just watching.
Yep.
Yeah, me too.
And I knew he lived.
Yeah, me too. Yeah. Especially that part where he like steps over and like he slipped during training. He's like, I have to step.
That was crazy.
What are you doing, dude? Like, time out. Just,
like you would have died if you had not been tied up then. So go do it anyway.
Yeah, so just like that's a different level of fear. So I called Alex and I was like, hey, Alex, how do I land on a rock? And he didn't answer. No, we haven't contacted any rock climbers for this. That'd be pretty cool though. The way we land on this is actually pretty simple to think about. It doesn't come from me. It's been theorized a lot, and it actually comes from one of our former companies before us and some of the work they did, which is we're going after iron nickel rich asteroids, right? Called metal asteroids. And the nice thing about them is they're magnetic. So we use magnets. It's a pretty simple way to think about how we land on one of these bodies. It actually makes the physics and the algorithms behind landing, while I shouldn't call them simple, much, much simpler than actually landing on any other body in the universe. So we have no harpoons. We have no shit out of ESA with hooks and grapples and, whatever. It can't be complicated. Look, we have to be a cheap, low-cost spacecraft, and we got to land on something potentially up to 10 million miles away. I got to make it be really, really clean and easy, and that's just done through magnetism.
Okay. Once again, my vote is still harpoons. From Siddhartha, how much AI is currently integrated into AstroForge's operations? Would it actually help us meet deadlines or speed up iteration, given our mission is all about fast learning and rapid execution?
Yeah, I could talk forever about this because I think there's a whole bunch of notions here that just don't make a lot of sense. So when we talk about AI, what are we talking about? I think we need to actually clarify this. And so we talk about AI when I talk about ChatGPT or LLMs. The honest truth is, what does it do for us? Like, it actually helps spell check my emails really well. It helps us spell check a lot of the writing we do and maybe even organize our thoughts to some extent or go through this but that's about it. We have not come across LLMs that are able to design boards or embedded software. To some extent it can do, but with embedded software, because you're so, keep in mind, our software, we're very, very architecture dependent. And in some cases, like, we have all these differences in it. It will help us to some extent. I think that's probably where we get helped the most. But even there, we're very cautious. We've caught quite a few errors with it. And the reality is the cost of an error on a spacecraft is extremely high. We're not deploying a website where I can be like, oh, shit, wrong color, let's fix it. Like, we would fail. And so on some extent, we actually try to minimize it on the software side. Now, when it comes to ground software, we use it all over the place because it's easy to verify, right? That's probably an area we use it highly. Other than that, we really don't. But when we use this classic, about 5 years ago, we started using this term AI, and it was actually referring to machine learning algorithms. So you probably remember when we used to say like AI/ML, machine learning all over the place, whatever that meant. And then before that, we used to use a really, really crazy word. We used to call it statistics, right? And so do we use statistics? Like, yeah, we use statistics all over the place. That goes to how we locate where targets are in space, how we use cameras, how we use machine learning or machine vision to lock onto targets. Like that we use at a very, very high level. And we use some really, really advanced estimation algorithms to do some of our tracking. But that's how I would break it down. As much as I love ChatGPT and I think it's really cool when there's a lot, it's not very helpful in designing hardware at this point in time. And I hope that will change because it would be so cool to actually just get rid of the entire avionics team and do it with AI.
All right. Well,
I actually had a good use case for AI recently.
oh, okay. What was that?
I used it to make the ESD training slides. But
I'm not showing up to your training.
but I can 100% verify all the information on it.
So much fun tomorrow then. All right, cool.
I look at it as like a junior intern that I don't trust.
Yeah,
right?
it's a perfect. That's exactly how I think about it too. It's like high potential, low amount of trust so far.
Yeah.
Yep. Okay. All right. From Andrew, this is not even two-parter. This is multi-parter. Hi guys, love the cast. I have two general categories.
Love the cast. Hold on. Love the cast. Everybody usually says
be talking about
love the
guests.
pod, and this guy's like, nope. I'm going to use the second half of that word. All right, I give you credit, Andrew. That's awesome.
Yeah, I interpret it as like cast of characters, not necessarily like the actual broadcast.
Well,
of
then
this,
fuck that guy because I haven't been here for the last 5 weeks, so that's rude.
All right. So his questions are about the TVC system. Why does TVC need to be used for navigation at such low thrust levels? Couldn't you just use the reaction wheels to adjust your attitude and that could control the orientation of the thruster?
So I'm going to assume Andrew works on rockets because TVC is usually called thrust vector control.
Yeah.
Right? And thrust vector control is very commonly used on like first stage of a Falcon 9, all their gimbal thrusters that are on this. So there's a gimbal and there's usually two actuators that are hydraulically controlled from the power pack that will allow you to change the position of the nozzle to correct the steering of the rocket. Right? Now, can we control our spacecraft with just reaction wheels and desaturate with just reaction wheels? And what we would desaturate on, so everybody knows, is we have two EP thrusters that are pointed out the bottom of the spacecraft. They're not going directly through the center of mass because they're not in the center of the spacecraft. And as you use fuel, the CG of the spacecraft changes, so you're never going to hit it right on. So we will increase our reaction wheel spin and have to desaturate at certain points. Can we do it with just the reaction wheels? Yes, we absolutely can. But it's really inefficient to do because you actually, with EP, you have to spin the spacecraft by 90 degrees, fire it to desaturate, spin it another 90 degrees, fire it. It's very complicated. It would take a lot of thrust, and it would kill the amount of usable delta V that we have on the spacecraft to get to the target asteroid. This is why you see all EP deep spacecraft gimbaled. What we're doing with the gimbal is actually adjusting where the thruster is facing by a couple of degrees to make sure that it goes as close to the CG as possible or start to desaturate the spacecraft.
So, excellent answer. And that leads up to his second question, which is, I'm curious why your gimbal has 3 actuators. It seems like using 2 would be just much simpler since there will only be one solution for any given vector command. This is the configuration I see on SpaceX's Merlin engine, for example. So the question is, why 3 actuators, not 2?
The reason we have 3 actuators on the gimbals we use is because there's not a pivot point in the middle. It's 2 rings. So when you have 2 rings like that, you need 3 actuators to be able to control 2 axes. If you just had 2, you could only control, think of it as there'd still be a center line no matter how you drew those 2. So you actually need 3 to give it the X and Y degrees of freedom. On something like a Merlin, a Merlin, the gimbal in the middle is actually a pivot point.
Yeah.
And the TVCs are able to affect one in the X direction and one in the Y direction. But because of the 2 rings, we can't do that from a geometric standpoint.
Got it. Okay. And last question from our esteemed head of avionics, Chris.
So a callback to the first question from the mailbag.
Okay.
How do we know that the asteroid we're going to try to land on is metal?
I think the short answer is there's a difference. To be clear, we're never going to have perfect clarity on any object in space we go to until we show up. So if I'm going to say we know with 100% certainty it's metal and it's higher than 70% iron and it's going to be magnetic because of that and blah, 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 I'd just be lying to you. We don't actually know that's true. We do have, as you know, a whole grouping of asteroids, and we have probabilities on how likely they are to be M-type asteroids. And we do a lot of spectrometry data, a lot of measurements on them to try to figure out which ones are going to be metal or not. But it's not printing out, this is 74.5% iron and this. And so how are we going to know? If we actually land on it. If we don't land on it, it wasn't metal enough. We hit it and bounce off. And I think that's kind of the risk posture and that we have to run a company with. You can go, even when you look at the Psyche mission, right? It's NASA's, really expensive mission, Class B mission to an asteroid called Psyche 16. It's an awesome mission. We're very close with that team. Their thesis on the actual asteroid itself has changed multiple times over the last decade as they continue to get new measurements. There isn't some like holy grail kind of algorithm we can plop into and say, oh, we have this asteroid, we found it, here's the name, exactly what it is and what's the breakdown. We haven't explored that much. And so part of this is going to be fingers crossed it sticks. We'll have high likelihood it's going to stick, but I think you also actually learn a lot if it doesn't. If we hit it and bounce off it, like I tell you guys all the time, right? If we hit it and bounce off it, guess what? We made it to a fucking asteroid. That's pretty awesome. And while I hope we land on one, I'm also happy with hitting it.
Yeah.
Awesome. All right. Well, that is episode 39. Thanks, Chris, for telling us how you design electronics to survive all the crazy shit that happens in space.
Hold on. I got a question.
This is
this is like a boomerang.
I got a question.
Going truly off script now.
For Rachel. I just noticed this. As I look at the cameras facing us, Chris has this beautiful new camera. Chap, you got a mediocre camera. And I got this like ghetto little piece of shit that we found. What is up with this? Why don't I have the good camera?
I got to pick the seat when I got here.
What? It should be my camera because it. Okay, I was just thinking that I got the lowest quality camera, but I'm glad that I'm supposed to get the highest quality camera. It's just oriented wrong.
Also, just for everybody's context, welcome to the team, Jack, who is the disembodied voice from the background that just came onto there. So yeah.
Jack, fix the fucking cameras. This is some bullshit, okay? Jesus Christ.
Wait, we'll have to trade seats then, so I still have the nice camera.
The camera angle is definitely the thing that's holding us back.
Also, these KFC lights. I feel like these are like what when you go to like the grocery store and they're like under the hot lamps. Like this is.
I'm gonna have spots in my eyes for days.
Seriously, dude, I'm going blind. What is this? Where did we get these things from?
Oh, the trick is you just gotta look. You gotta look down.
Yeah, but I keep looking at him now because I'm talking
Well,
about him, and I keep going blind.
That's user error. That's just straight up user error, man. Just gotta look down.
Fuck.
All right, that's it. We're out. This is episode 39. Thank you for tuning in. Thank you to Chris for how we design electronics to survive in space. We will be back next week. Thank you.
I think I burned my retinas after looking at him more.